Good morning, everyone. So we'll continue our discussion on bipolar junction transistors. So last meeting we ended here. We defined the relationships between BJT parameters, especially BJT currents and BJT voltages. So katong mga relationships will be defined by these formulas, most importantly by these three formulas. Formula 1, Formula 2, and Formula 3. And kining Formula 4 again, it's derived from the first two formulas. So let's try to review some concepts that we have discussed last time. So here are selected key terms. You could review this one. So slides, I will upload this one on eLearn, of course. So let's try to answer these questions. Example number 1. The region on the characteristic curve in which the current changes only slightly with an increase in VCE is called what region? The current changes only slightly with an increase in VCE. Okay. So what region will this be? If mag-increase ang voltage sa collector emitter, change po ang current sa collector. No? This is the active region. The active region, letter D. So that is D. This one, beta DC is defined as the ratio of beta. Ito sa atong mga formulas. Formula number 2, IC equals beta IB, or if you rearrange na to, beta is equal to IC over IB. Okay, so IC over IB. Collector current over base current, letter A. Answer is letter A. Next. When the BJT is in saturation, the blank. All of the above siguro. The collector current does not change with an increase in base current. Yes, this is true. Base current cannot increase. Dili na ba mag-increase? No, mag-increase gyapon, no? True man ng A. So B cannot be true. So dili siya, all of the above. Collector to emitter voltage is maximum. No. Collector to emitter voltage is 0. So the answer is only A. Collector current does not change because it has achieved maximum value. When the BJT is cut off, this is when cut off. I is equal to 0. I is equal to 0 and VCE is equal to maximum. Voltage from collector to emitter is near 0. No, this is wrong. Collector current is near 0. Correct. Base emitter junction is forward biased. No. For cut off, kanya akong gipang sulat nala ni tanan dito sa slide sa ako lang gipang review. For at least is what delay for convenience. But nanita ng slides, of course. For cut off, both the collector base and base emitter are reverse biased. So no, this is also not true. So true one si B, so this is not true. The answer is B. Near 0. Well, actually 0 manggid, no? Na mo gid current gamay, no? Near 0. Yeah. Or if we could assume na not near 0 but exactly 0, like this one, exactly 0, pwede lang po D. D siguro gid ang answer kung i-approximate na to. Siguro kung natin microscope, kita na to na mag-gamay current malilik. Pero for approximation purposes, you could say that IC is equal to 0. So ano lang di above siguro. The lower end of the DC load line touches the x-axis at cutoff. Yeah, cutoff. Ako lang ni A-conjugate, no? Tanawon. X-axis. Awa ha. Ato man yung na-discuss last time. Here, oh. Basta mag-touch ang DC load line. So X-axis, that's cutoff. Because cutoff region here, the cutoff region is below the X-axis. Okay. Nalagyan natin ng slides ang answer yung mga questions. Okay. Number 6. The circuit shown, the base current is di natin ni ma-solve ron, no? I think mo ni siya atong lesson this morning, how to solve for amplifier transistor currents. So, skip lang sa natin eh. Same with this one. Saturation current. Yeah, hindi natin ni ma-solve pa. Optocoupler is a single package containing not 2 transistors, a LED and a phototransistor. I think this is the answer. Phototransistor and relay, no, it's not a relay. An LED and a relay, of course not. So the answer is B. Transistor package at this TO3 cases. Technical man kayo ni. Mo-refer lang siguro pa sa very last slide. This one. It's this one. See. Siya dire. TO3. Trivial. Dali lang na siya ma-refer. Okay. So having these in mind, let's now learn how to solve. So solve for the amplifier currents and voltages. Or in other words, let's learn transistor biasing. Okay. DC biasing. BJT. BJT biasing. So unlike the biasing with diodes, when we try to bias BJT amplifier or BJTs, I do a process. So it involves 2 processes. We have the DC biasing in the DC domain and AC biasing. So this morning and next meeting, I think we'll focus more sa DC biasing. 2 weeks from now, I think ang AC biasing. So we'll only my space transfer lang this last. So next week we'll only be meeting on Tuesday. Now kaya holiday naman sa Friday. So next na itong meeting after Tuesday next week will be Tuesday next week. Kung na siya reminder. Okay, so okay, thank you. So BJT biasing. This morning we'll focus on DC biasing. How to properly bias BJT. So when we bias BJTs, we'd end up with 2 possibilities, or 2 operations. Either it could become an amplifier or a switch. But of course, I think ako na emphasize last meeting, either amplifier or switch. For the most part, we will only focus sa pag-bias BJT as an amplifier. Sa switch, i-touch gap na ito na siya. Pero technically, mas dali mo na siya. No? Mas complicated, no? Or mas complex ang pag-bias sa amplifier, as a BJT as an amplifier. So when we bias BJT as a switch, muna lang po sa switch, again, remember that it will be in both the saturation, of course not at the same time, no? But both sa saturation and cutoff regions. And mag-interchange sila. At one instance, nasa sa saturation, another instance, nasa sa cutoff. Meaning, at saturation, both the collector base and base emitter regions are forward biased. Okay. Sa cutoff, both of these regions are reverse biased. Reverse biased. So for amplifier, the collector base region is reverse biased, whereas the base emitter is forward bias. So naka-forward bias siya ang base emitter. And remember that the base emitter voltage for BJT in this operation is at 0.7 volts. So kana naka-memorize na gina siya daan ha. So actually that's the second na to formula, diba? No, third. Ang first two defines the currents. Okay. Siguro nila. Yeah, so let's try to solve or analyze amplifier circuits. So we have multiple DC biasing circuits available. Ako lang isot dire. Okay. Actually, dagan na klase-klase na DC biasing circuits. The most common one is the fixed bias. Okay, fixed bias, which is the most unstable of all biasing circuits. It will work, but compared to the others, it's not very stable. No? Maybe I'll expound the stability later. Next nga more stable compared sa fixed bias. Less stable gapon compared sa others, but alang lang compared sa fixed bias is the emitter bias. One of the very stable configurations or circuit is the voltage divider bias. Voltage divider bias. And so much more actually. No? Napod gani mga biasing circuits na wala tayo definite name. So ito lang siyang gandan as miscellaneous. No? But we'll try to focus sa mga familiar lang na mga biasing circuits like this one. So this morning we'll start with fixed bias configuration. So what does a fixed bias circuit looks like? So let's draw our transistor first. Our BJT transistor. NPN. Okay. Dili atong collector. This terminal is the collector. This one is the base. This one is the emitter. So how many external circuits do we need to connect to our transistor for us to create a fixed bias configuration? Actually, only two. Two resistors. So si emitter, connect natin siya directly sa ground. Sa base, mag-connect tag isa ka resistor that we call RB. And sa collector, pupuntang ko tag isa ka resistor that we call RC. Okay. And both ang mga resistors, i-connect na to sa isa ka common nga voltage source. That we call VCC. And it's always positive. So this is the fixed bias configuration. Actually, napagid capacitor here and capacitor here. So these capacitors restrict at least the DC analysis only sa diri nga portion. No? So if we try to solve the reactances of these, I think remember man sila ang term, reactance. If we solve for the reactance of a DC source, DC source, ilan man ang formula sa reactance? 1 over 2 pi f, 2 pi f RC, I think. Yeah, I think mo ni siya 2 pi f RC, if I'm not mistaken. Anyway, for DC for DC sources, frequency is very low, approximately equal to 0. So if 0 ang denominator, ang resulting reactance is very high, close to infinity. So if very high siya nga reactance, or meaning very high nga impedance, so it's as if we have a very large resistor here, So pwede natin siya i-erase because it has a very large resistance right here. Nga dili maka-influence ang DC current outside sa atong circuit. So that's just for formality. Ako lang i-explain nga nung pwede na natin ignore ang capacitors as of this time. So more ni ang atong i-focus for fixed bias configuration. Okay. So aman to atong mga currents, or our currents. We have IC, IE, and IB. So IB, because this is NPN, again, because NPN siya nga BJT, IB goes inside. Same with IC. So this is IC. And si IE is not there. Naog. Pagawas. Okay. Remember, ang arrow, pagawas siya. So, pagawas si IE. IE is IB plus IC by virtue of KCL. So this will hold true. So there's a relationship between IC and IB. Of course, we know that to be IC is equal to beta IB. So muna na yung mga tulo na to ka relationships. This one, and that one. try to solve for all the other voltages. So siguro first ato sang i-withdraw, no? Let's try to withdraw this one. If dili pa ta comfortable mag analyze or tan-aw sa ingani nga klase nga circuit, pwede na to i-withdraw, no? So how do we do that? Pwede na to ni siya i-bulag, no? Separate na to ni. As if natay duha ka VCC or duha ka DC sources. No? Yan na. So without the same flag value. Okay. To do that, no? Meaning si RB is connected to a separate DC source from RC of the same value. So if nga na, it could look like this. Yan na. And because these are just wires, pwede natin siya i-bend. No? I-straighten natin itong mga wires. Hindi na mag-matter. Hindi na siya maka-affect sa itong analysis. So, it will look something like this. Si emitter connected sa ground. And we'll use the symbol that we're comfortable with sa DC source. This one. Connected sa ground. No. Okay. So I think mas familiar ni siya nga type of circuit. So this is RB. This is RC. This is VCC. This is VCC. Same value. Okay. So meaning, we could create two separate KVL equations. Isa here. And another one here. Okay. So we have two separate KVL equations. Focus sa delay. If mag-KVL ta sa left na part, try to observe as VCC minus the voltage RB minus voltage VBE, then ground naman, so equal to 0. So ako itong i-rewrite. VCC minus voltage across RB minus VBE equal to 0. Okay. Si voltage across RB by virtue of Ohm's law, by virtue of Ohm's law, V cos IR. So pwede na ito niya siya simplify as I, what's the current across or going through our RB. So IB. Where is IB? Diba, this is the current IB going current nga gapasod sa base. That is also the same current nga galahos kay RB. So IB, no? IB times the resistor RB minus VBE, which is 0.7, diba? So kanina memorize na siya, dapat nato na 0.7 volts na siya. So actually class, kung atong tanawon, VCC is given, VBE is constant, 0.7. The value for the resistor is of course given. So one equation, one unknown, masolve na nato na si IB. Next, the KVL equation. Here. So VCC minus voltage across RC minus VCE, voltage sa CE, equal to 0 after sa emitter, ground naman. So VCC minus VRC, voltage across RC, minus VCE is equal to 0. We know that the voltage across RC is just the resistor RC times the current IC. So rewriting our equation, VCC minus IC RC minus VCE is equal to 0. So these are the equations that will help us solve the BJT currents and voltages. This one and this one. Okay. So itong i-derive na, no? So for each configuration, I mentioned earlier, fixed bias, emitter bias, voltage divider bias, and etc. etc. Kada isa ani nila, lais lang mga KVL equations. So actually, yeah, ipang-derive yun na sa tagsa-tagsa. Lahi man. No? So these formulas, at least kaning duha, these formulas only work for voltage divider bias. For the emitter bias, lahi na pod nga KVL equations. But no matter what configurations we have at hand, mo ni sila nga formulas, at least these 4 formulas are common to all. So maski fixed bias pa na siya or voltage divider bias, kaning tulo nga formulas, or I mean kaning upat, magamit yun eh. Okay. Okay, let's try to solve an actual example. Kana kung pag-circle og sa transistor class mag-char-char na siya. Palagi na siya yung significance. This. Masyado na tanawon. I think wala yung given, no? So for example, we have this amplifier circuit. No? So if mutana mo, is this a practical na circuit? Yes, of course. If mo connect the delay og input signal, no? Let's say for example, microphone. Microphone delay. Then delay na to i-connect ng atong speaker. Will this work? Yes, this will work na. This already is a working amplifier circuit. This is siguro as nice, no, as more sophisticated amplifier circuits, but nonetheless, this will work. No? Amplifier circuit din mismo. So pwede lagi data maka-create amplifier using only a transistor and 2 resistors. No? Pwede lagi yun. Siguro kalat-kalat gid ang kuhaan eh. Pero pwede na, no? Pwede na. So sa tayo pang solve ani. Solve for IB, IC, IE, and VCE. Kana lang, no? How about conserve VBE? No need, given. How about VCB? No need gapon, diba? Because VCB is for amplifiers, reverse bias, remember? For amplifier, naka-reverse bias ang collector to base, at ito na gina-ignore. So no need to solve for that one. Isa lagi ka voltage atong gina-solve ang VCE. VBE is already given. Or I mean, is constant. So more na siya. No? So for IB, IC, IE, and VCE, asa sa mga kita. This is IB. This is IC. This is IE. And from collector to emitter, this is the collector. Ating emitter. Yan nato i-measure si VCE. So what if natin multimeter? Ito na to ang isa ka terminal delay. O isa dito. So muna siya si VCE. Yan nato ma-measure. Across the collector and emitter regions. Okay. Yeah, I think good na ni. So if we do not need to analyze na, we just need to invoke these formulas, no? So kung i-memorize ninyo, so kita magyapon, no? No problem. These formulas. If we take down, if we take note of na ninyo nidaan, and then i-invoke lang ninyo later sa mga examples, so kita magyapon, no? If i-memorize ninyo, or na may copy daan, so mas maayo. If wala, no? Pwede lang mo mag-derive, no? You could derive those equations directly from the circuit. So kung hindi na ito mag-derive, ma-derive na ito kanina, ito na ito lang ipang-invoke. I think memorize naman sa nako sa akong nahuna karon. So gamit ta sa kuan, no? First KVL equation. VCC minus IB RB minus VBE equal to 0. Okay. VCC is given 12 volts. IB is not given, so unknown. RB is given to 40 kilo ohms. So to 40K minus VBE, memorize na dapat 0.7. equal to 0. One equation, one unknown. Si IB ang unknown. You could solve for IB. How much is IB? If you have the calculators with you could solve this one. Check to solve. Nasa mga 47 microamperes. If I'm not mistaken. Check down. It's the same answer.
Yes, sir. 4.7.
Yes, sir. Yes, sir.
4.7 to the negative 4.
Negative 5, sir.
Negative 5. Kung na-decimal, pila niya? 1? 47.1?
Yes, sir. 4.7.
Sige, sige. Okay, thank you. Microamperes. So, it's common to encounter IB or the base current sa microamperes na range, no? If makakuha kayo tag 1 digit na IB na nasa milliampere na range, pwede na tayo mag-doubt sa itong answer, no? For example, 1 milliampere na IB. So let's like to check our solutions again kay basig na sa iyo ta. Dili na siya common. Kung wala gyud din mo gina siya. So maybe basig naka-saturation na tong transistor, pero it's time to doubt our answer kung naka milliamperes na siya, then naka 1 digit. So common ni siya for IB, no? Mga 2 digit na microamperes na range. So okay, this is IB, no? Solve na to IB. Pag masolve ngayon si IB class, dali na rin na masolve si IC o IE, no? So we just invoke these formulas that we had from the previous meeting. Katong mga relationship between currents, no? Na dapat nagitay copy gid siguro ani or na-memorize na nato. Di magpasalisod di memorize gid at least kaning first 3, no? So IE is equal to IC plus IB. Dili pa ni ma-solve, di pa ni magamit. Matay IC. Number 2 siguro IC equals to beta IB. So IC is equal to beta IB. Given man gining si beta, 50. So 50 times IB of 47.1 micro. Nasa mga mili ang mugawa sa ani. So IC is more or less equal to 2.35 milliamperes. Ito answer nyo kaniya, directly multiply by 50 la. No? 2.35 milliamperes. Same tag-answer.
Yes, sir.
Thank you. So 2.35 milliamperes. IE, no? What if, sir, kung gamiton ning ika-5 nga kuan, no? Formula, approximation, pwede ba? Well, pwede ba, no? Di man kayo siya gyud dako og changes. But kung ano na sa nato ang kuan, no? Ang more accurate nga numerical value. Technically, no, kung gusto nato, pwede lagi ni IE diretso approximately equal to 2.35 milliampere. Diretso, no? Pero ato sang kwaon, no? Ato sang kwaon. Ato makita nganong valid dato siya nga approximation. Let's solve for IE. IE, again, based on formula, is equal to IB plus IC. Remember, lahi og unit si IB ug IC. So if you add na to sa calculator, make sure nga i-consider na tong units, no? Example, this one. 47.1 micro, which is times 10 to the power of negative 6 plus 2.35 milli times 10 to the negative 3. So careful lang mo. Kaya basig ma-add ninyo dito ang 2.35 plus 47.1. Kung gawas kay mga 49.35. So sayop na. So how much is IE? Dapat approximately equal to IC. Mga 2 point, pila ba ni?
39, sir.
39. Okay, 35 plus 4 man ni siya. 35 plus 4. 0.04 milli maning 47 micro. So 2.39. Diba? Dual-dual ba? So ato na yung approximate as 2.4. 2.4 lasad ni siya. So 2.39 milliamperes. That's the more accurate na numerical value. Okay. So we already solved for the 3 transistor currents. So far, before I proceed, any questions? Saya na? Kaya na? Mas simple siya, no? Kaysa sa BJT? Sa diode? Would you agree?
Sir.
Lagi, maski ako, no? Maski ako masensay pa mag-ini kaysa sa diode. So iPhone, milalagid magdala. So di mata maabot sa point nga kabalo taon sa formula gamiton kung lahat na to gi-analyze daan. So important gyapon nga i-analyze. Pero kung sige tag-practice og solve og mga problems, kadugayan maana dayon ta kabalo dayon taon sa mga formula ang paggamiton. Okay. So yeah, we've already solved for the 3 important transistor currents. Next is VCE. Why is VCE important? For one thing, VCE is important because dito nga terminal na to i-connect ang load, no, sa collector. So dapat mag-match ang voltage. And another thing, dapat dili pod kaayo dako ang value ni VCE or the collector emitter voltage, because if large siya enough and i-multiply na to voltage mo to, di ba? Multiply na to siya sa current nga mag-pass to sa transistor, which is IC, and mulapas siya sa active region, meaning na siya sa breakdown region, there's a possibility, there's a very big possibility na magubagi ng atong device, atong transistor. So that's why we're trying to solve right now for IC and VCE. So we're solving for VCE. We'll invoke the second formula, this one, the KVL equation from the right side, no, or right portions of circuit. So VCC minus ICRC minus VCE. So VCC minus ICRC minus VCE. Yeah, equal to 0. Given VCC 12, IC is na obtain na nato 2.35 milli. RC is given, I believe it's 2.2 kilo, diba? Sa circuit. Pwede na natin siya i-shortcut kanina sa calculator, basta milli o kilo ang i-multiply. Cancel out ang ilang mga unit. Diba? So 2.35 times 2.2 lang na siya. Pagbo sa calculator. Mag-cancel out si milli o si kilo. So kung dili na sila milli o kilo, ayun na lang, no? Ayun lang i-shortcut. Minus VCE of, wala, unknown, no? Of course, VCE ang unknown dahil equal to 0. So, we can solve for VCE. VCE equal to, pila ba? Pila class?
6.83, sir.
Very good. 6.83 volts. Okay, final answer. Yeah. So added lang ako an information. We could solve for the power consumed by the device, PD, which is equal to IC BCE. So muna siya formula sa power dissipated sa device. The power that's coming inside the device, the transistor, and the voltage drop sa collector emitter na terminals. So it's how much is IC? 2.35. So it's 2.35 milliamperes times 6.83 volts is how much? Milliwatts. Milliwatts ang gawa sa anin, for sure. Pila class?
16.05, sir.
16.05 milliwatts. Okay? So, gamay lang na siya nga kuan. Information kasi significant sa ani. After performing analysis, in practice, after performing analysis, we'll try to check sa specification sheets if wala ba naabot o wala ba nalapas, no? Wala ba nakalapas ng 16.05, no? Okay. Wala mo ko yung actual specs dito sa atong transistor. Itawag sample, no? Sample specs sa transistor. So this is an example of a specification sheet of a transistor. Ang iyang part number is P2N2222A. This is the most commonly used amplifier transistor, general purpose transistor. No? So when you say general purpose, there are more specific kinds of BJT transistors out there. So this is what I was talking about just now. Look at this, maximum ratings. Total device dissipation. So ning kon ECTA. I think mo siguro na ambient temperature niya, I believe, no? So ambient temperature. Alam mo kung sa ning PC. Mo yung pinakauna, so I think mo ni siya, no? In practice mo yung gina-refer na mo. So PD, nadili 625 milliwatts. Layo pa, no? Dili pa ni maguba ang atong transistor kung gigamit nato as ingani katong sa gisolve bitaw nato kanina. 16 milliwatts naman to, di ba? 16 milliwatts. So kani 625 layo pa. No? Dili pa siya maguba. Itry daw 625 divided by 6. Sige daw class, 625 divided by 6. Tingnan lang ko pila mo gawas.
104.16, sir.
4.16. So kung atong BCE is more or less manggod kung pila ang supply, 12 volts man to ganyan, di ba? More or less ang BCE is mga katunga ana, mga 6 volts. So itong na-solve na to ganina, 6.83. Okay na to siyang value, no? More than sa half sa voltage source, pero okay lang na siya. So 6 lang akong gigamit dito para for simplified lang nga calculation. So gipa-divide na ako ang 625 og 6. which is ang akong assumed nga VCE. So, pila to? 100, pila to?
104.
104, no? So, layo pa kaayo ang atong 2 milliamperes. So, kung maabot na natin 104, which is ako ang kayo ni kay, kung maabot og 104 milliamperes ang atong IC, diha na nga time nga madaot ang atong device. So, katong 2, alay kay ito, no? Bisan pag 12 siguro, no? 12. Ito na to, 625 divided by 12. So, meaning, tanan nga voltage ni battery is gikaon kibali ni device, no? Tanan nga voltage ni battery 12 volts gikaon ni device ni VCE, so VCE is equal to 12, no? At this time nag saturation na siguro siya, I guess. So 625 divided by 12 is 52, no? So most probably 52 iyahang saturation current ani. No? Once mabot og 50 milliamperes malagwa na kayo, no? Delikado na siya. Nanay possibility maguba ang atong device. So, malang significant sa ani, no? Just telling you right now para at least ma-aware ta. Say significant sa solving for IC, VCE because pang-check na siya. Check na to na siya sa specification sheets kung layo pa ba sa limit. And this is the limit, 625. So, layo pa yun. 16 man to. So, layo pa. Whether amplifier design, no, or any kind of circuit design class is a really good engineering practice to get to know how to read specification sheets. So, dili lang sa electronics, masin sa inyong other future subjects, masin sa inyong mga majors, it's good engineering practice to refer to specification sheets and to read the specification sheets. And of course, to know how to read the specification sheets. May ano bilaw, mga graph dire, at least couple taon sa pagtanawanin nila. So mga most basic is kanang nasa front page gives a specs, which is this one. Maximum collector emitter voltage na is 40. Collector base is 75. Or negative 75 siguro ni kay reverse bias, no? Maximum emitter base voltage or VBE is 6 volts. 0.7 man ang atong gina-use, di ba? So maximum na ni siya. Yeah. So kato, no? At least natin na-learn something new today. So baliktad dire. So these are the values, no, na itong na-obtain with a beta of 50. I'll give you another situation. What if si transistor na to is naguba, no? Or need i-replace? Nasunog, buto, no? Or for whatever reason. So kinahanglan to siya i-pull out, kinahanglan to i-desolder, then itataglain. But tungod kay naguba siya, di nato mabasa iyahang part number. No, we do not know what kind of transistor is this. So i-replace nato siya something else, no? Kung man takabalo nga iyang beta originally is 50, no? Let's just say takabalo nga beta 50 ang beta originally. So we have a replacement transistor na iyang beta is now 100, no? So your task right now, siguro assignment na lang, no? Try to redo what we have just performed. Meaning, i-replace lang nyo si beta o 100. So, try to observe the changes. No? Try to observe the changes. Try to solve for each current and currents and voltage, the percentage difference. Kanaton sa layo, no? For sure, sa IB is not beta dependent man. So, So you'll still obtain the same value for IB. So 0 ang percent difference niya ni. So IC, dili na dayon. Maybe 50% siguro difference kay 50% man eh. No, ang increase from 50 to 100. So how will we solve for percent difference? It's percent difference formula. So old minus new absolute value ni siya ha. So old value minus new value divided by old value plus new value times 200. So that's the formula for percentage difference. So I expect later, assignment lang siguro ni, yan ang mo gawas. After solving this again, after redoing, butan nyo sa table siguro, no? IB, IC, IE, BCE, sorry. Mistake. Beta equals to 50, beta equals 100, and percentage difference. So the same naman sila. The same lang volume of quadrate for sure. So I'm sure 0 niyang percent difference. Yeah. So try to fill in all the others. Try to observe if dako ba or gamay ang percentage difference. Actually, you could try it for another beta, no? For 150, let's say, for example. Pero yun lang sila ng extra pagkakuan. Exercise. For your task, which is very simple, just redo everything that we have done with the beta of 100 and solve for the percentage difference. Okay? Is it clear?
Yes, sir.
Sige.
Yes, sir.
Sir, dili na pilot ang power dissipated, sir.
Ayan na. Kana lang sila.